My name is Daniel Manuel, and this is the Black Hole Lab. Introduction. The purpose of this lab, in part 1, is to estimate the mass of a black hole by analyzing the star orbit with a mass of 2.0 times 10 to the 30 kilograms. The found mass of the black hole was estimated to be 1.412 times 10 to the 34 kilograms. In part 2, the purpose is to simulate the motion of a spaceship taking off from a planet orbiting the same black hole in which the mass was calculated for in part 1. The spaceship should take off in the same direction as the planet's motion and not crash into either the black hole or the planet, and the goal is to find the initial velocity in order to do this. The initial velocity was determined to be the vector negative 3.5 times 10 to the 7, 4.5 times 10 to the 6, and 0 meters per second. The fundamental principles used in this lab were Newton's second law, or the momentum principle, and Newton's law of universal gravitation, which will have related equations in the next slide. The parallel and perpendicular components of net force were also used. These are the formulas for part 1 and part 2. Part 1 shows deriving the parallel and perpendicular force components from the change in momentum over change in time, and part 2's formulas relate to finding the force of gravity and the position and velocity update formula. Models for part 1. The top video shows the program in motion as it calculates the black hole mass as the star makes its orbit. The bottom image was taken while the program is running, and you can see the net force pointing towards the black hole in orange, the cyan arrow representing the net force perpendicular, and then the pink arrow representing the net force parallel. The code for part 1. In lines 164 and 165, we calculate the initial and final momentum vectors using the formula P equals mv. In 168 and 169, we calculate the change in velocity and change in momentum. In line 172, we calculate the change in momentum over time. In line 175 calculates the net force by setting it equal to dp dt, since the net force is equal to the change in momentum over time. Lines 178 to 180 calculate p hat by using the norm function. The next line calculates the change in the magnitude of momentum over time, and the line under that applies both previous lines to calculate the change in momentum over time perpendicular. Line 183 finds the net force parallel by getting set equal to the previously calculated change in momentum over time parallel. Line 186 calculates the net force perpendicular using the following equation. Net force is equal to change in momentum over change in time parallel plus change in momentum over change in time perpendicular. And then you solve for the perpendicular component. Line 189 sets the net force perpendicular equal to the change in momentum over time perpendicular. And then lines 203 to 207 scale the arrows so that you can visually see the net force perpendicular, and net force parallel on the simulation while it runs. Models in part 2. Part 2 of this lab simulates the same black hole, but adds a planet orbiting it. That planet has a rocket that launches in the same direction of its orbit. The first image shows the trajectory to fly by the black hole and the x and y speed that it took to do that, which is negative 3.5 times 10 to the 7th, 5 times 10 to the 6th, and then 0 meters per second. The second image shows the spacecraft performing an orbit around the black hole without crashing into the planet or getting overcome by the black hole's force of gravity. The vector velocity to do this was 0, 9.97 times 10 to the 6th, and then 0 meters per second. Magenta represents the ship, and cyan represents the orbit of the planet. Code for part 2. Lines 79 and 80 find the distance from the black hole to the planet and uses that distance to get plugged into the formula for the force of gravity from the black hole on the planet. Lines 82 and 83 do the same as above, except for the distance is from the ship to the planet, and the gravitational force is from the ship on the planet. Lines 85 sum those two gravitational forces for the net force on the planet. Lines 93 and 94 are finding the force of gravity on the ship from the black hole from the distance of the black hole to the ship. Lines 96 and 97 are finding the force of gravity on the ship from the planet from the distance of the planet to the ship. Line 99 sums those forces on the ship. Then lines 105 to 109 use the velocity and position update formula to make the planet and spaceship move. What if? The rate of change in momentum is equal to the net force, but it could also be derived into parallel and perpendicular components of the net force as noted in the formula slide. In order to get the spaceship in an orbit around the black hole, I had to put the speed into the positive y direction and was able to do it with a velocity vector as follows. Possible sources of error would not be carrying all over the decimal points when recording the mass of the black hole in part 2. Thank you.